Today, we're looking at the final exam review for Math 11. And this is a comprehensive exam. That means that it covers everything we've done all semester. Now, this exam is a little bit different than the ones that we've seen before. The questions are similar, but the idea is a little bit different. So, normally I give an exam that has a 12 or 13, 14 part question on it. I've decided to not do that quite the same way this semester because of the way that Canvas works when you upload a file. If I gave a 13-part question, then you would have to upload one file that contained all 13 parts, and that might be difficult for you, especially if it takes multiple pages. How do you get multiple pages on one file? I mean, it's doable, but I didn't want you to have to stress out about it. So what I've done is I've broken it into separate individual problems, but it's the same idea. What I'm trying to do is show you in this exam how all the different things that we've done all semester long can come together in one cohesive whole, and how if you were actually performing a statistical investigation, how it might look. That's what these first several problems are all about. So let's go ahead and get into it. Questions 1 through 13 refer to the following situation. Recently, Blue Diamond claimed that there was an average of at least 130 almonds in their 16-ounce bags of almonds. You would like to test this claim. You randomly select 36 of their 16-ounce bags and count the nuts in each. The results are listed below. So we have 36 individual values representing how many nuts were found in each of the 36 bags. So that's our situation here. And we want to test their claim. But we're going to go through all the different things that we've done with a data set to get there. So question 1. Find the class width given 5 classes. So we have a formula for class width. That formula is that we do the max minus the min divided by the number of classes. Hopefully you remember that when we do the class width, whenever you get an answer, you always round up to the next highest whole number. Even if it comes out as a whole number, you go to the next highest whole number. So the maximum value here is 145, the minimum is 114, and the number of classes is 5. Now, I'm going to be kind to you in this exam. I will give you the data set in order, right? Because we've seen there are instances where we need to put the data in order. If you want to find the median, if you want to find quartiles, you have to have the data in order. And with a large data set like this, that can take an awful lot of time. I don't want you to have to waste time on your final exam putting the data set in order. That doesn't show me that you've learned a whole lot other than how to put some numbers in order. I would rather give you an ordered data set and see that you can do all the processes that we've learned. So what we're going to do here, we're going to subtract in the numerator. 145 minus 114 is 31 over 5, and 31 over 5 is 6.2. We round that up to the next highest whole number, so the class width is 7. So that would be your answer to question number 1. Question number 2. Find the class midpoints. Okay, so I've got a little table here that we're going to fill out. Before we can find the class midpoints, we have to define what the classes are. So if you remember when we were talking about classes and frequency distributions and midpoints, we said that the very first class always starts at the data minimum. So the data minimum here is 114. Then we take the class width and we add it to the minimum. 114 plus 7 is 121. That's the next lower class limit. Right? Don't put it next to the 114, it goes under the 114. We add 7 again and we get 128. Add 7, we get 135. Add 7, we get 142. So those are the numbers that begin each class. How do we know what the ending numbers are? Well, the first class starts at 114 and it goes to a number. The second class starts at 121 and it goes to a number. So that must mean that the first class finished right before the second class begins. So the first class ends at 120, right before 121. Once you get that first upper class limit, you can do the same thing we did with the lower class limits and add the class width. So 120 plus 7 is 127. Add 7 again, 134. Add 7 again, 141. Add 7 again, 148. You can see that the lower class limits are always one less than the next upper class limit. So once we've got the classes defined, we can find the midpoints. The formula for finding a midpoint is that you take the lower class limit plus the upper class limit and divide by 2. It's the average of the two endpoints of the class. So we'll do the first class here, 114 plus 120 over 2, which is 234 over 2, which is 117. So my first midpoint is 117. Now you could go ahead and do this for all the other classes, but you can also use the class width just like we did with the lower class limits and the upper class limits. So I'm going to do that. I'm going to take the 117 plus 7 and get 124. That's the second midpoint. Take the 124, add 7. That's 131. That's the third midpoint. Add 7 again. 138. Add 7. 145. And those are your midpoints, and that's the answer to question 2. Question number 3. Create a frequency distribution. We're going to rely on the same classes that we just defined. We don't need to recreate that work. 114 to 120, 121 to 127, and so on. Now normally we have this center column for a tally. Since your data is in order, there's not really much of a tally to do because that's where you're going through an unordered array and looking for data values that fall in each class. Here, because they're ordered, it's a lot easier. So from 114 to 120, let's look up at the data, and hopefully you realize it's those first 5 data entries. And that means the frequency of the first class is 5. How about from 121 to 127? Well, 121 to 127, that's a lot more data than we had from 114 to 120. It's all of those. 121, 122s, the 123s, 125s, 126, and 127. That's actually 12 individual entries. To go from 128 to 134, a lot of entries, also 12 actually. The entries between 135 and 141, there's 5 of them. And then we don't need to circle any here because what's left over at the end, those 2 data entries, are going to be from 142 to 148. So that's your answer for the frequency distribution. If you don't put anything in a tally column, that's fine, because we didn't need to use it because of the way that this problem was built. Question number 4. Find the mean. So, to find the mean, we need to add up all the data values. So let's add them up by column. The first column adds up to 497. The next column, 501. The third column, 506. Column 4, 507. Column 5, 510. Column 6, 517. Column 7, 519. Column 8, 523. And the last column, 528. Now you may wonder why those sums increased as we went, and that's because the data set's in order. So as we go farther to the right, we're getting bigger data values, which means that each column, since the column has bigger data values than the column before, we'll have a larger sum than the column before. Once we've got these values, we have to add them all up. And when we add up these 9 values, we'll use our calculator, and we get 4608. So to find the mean, which is our x bar, right, because this was a sample of 36 bags of almonds, make sure you're using x bar and not mu if it's a sample. So this is going to be 4608 divided by 36, because we had 36 bags of nuts. And when we divide, using our calculator, we get 128. I promise you, I will give you a nice mean, because at some point we're going to have to find the standard deviation. If you have a decimal mean, then that standard deviation calculation becomes a horrible thing to do. So I will give you a whole number mean. If you find a mean that's not a whole number, you made a mistake. Go back and figure out where you messed up. So 128 is the answer to question number 4. What else have we done? Well, number 5. Find the median. Again, we have the data set already in order. So there are an even number of data entries here. There's 36 data entries. And because 36 is an even number, the way we find the median is by finding the average of the 2 central entries. So which 2 entries are in the middle? Well, if it's set up like this, it's going to be the data entry at the end of the second row and at the beginning of the third row. Those are the 2 that fall in the middle. So my median here is going to be 128 plus 128 over 2, which is 256 over 2, which is just 128. Whenever you're finding the average of 2 numbers that are equal, that average is always going to be that number. So that's our answer to question number 5. Find the mode in question number 6. So again, with a data set that's in order, finding the mode should be pretty simple, because we're looking for the most frequently occurring data entry. So we look for something that happens more than anything else, and the one that happens more than anything else is 122. That happens 4 times. There are some other entries that happen 3 times, like 123 and 138, but nothing else happens 4 times. If you have a data set where 2 are tied for the most number of occurrences, then those are both the mode. And if there isn't one, or if there's a tie between 3 or more, then that has no mode. So make sure you understand those possibilities as well. But in this case, we have a mode, and the mode is 122. Question number 7. Find the variance. So the variance takes a while if we do it the way we did in section 2.4, where we would make a table of values. All 36 values would be there. We would subtract the mean from each one of those values to find our deviations. Then we would square the deviations, add those squares together, and divide by either n or n minus 1, depending on whether it was a population or a sample, and that would give us the variance. Here, we're going to use the calculator to help us, because we learned how to do these things on the calculator as well. So the variance isn't given in the one variable stat screen that we've seen so many other things on, but it is built into the calculator. And the formula for the variance, if you wanted to do it by making the table, is s squared equals the sum of x minus x bar squared over n minus 1. That's the sample variance formula. If it was a population variance, it would be over n. What we're going to do is we're going to press the stat button on our calculator, and that takes us to our stat screen here. The very first menu option at the top is the edit screen, and that's where it starts you out at. And our first option is to edit. We're just going to go ahead and press enter. That's going to take us to the stat list screen, where we can enter our lists. If you have values already in your lists and you need to clear them out before you begin, remember you can move up to highlight the name of the list, L1 or L2 or L3. press the clear button, and then come back down, and your list will be cleared. So what we're going to do is we're going to take all 36 of these data entries, and we're going to enter them into L1. So when you're all done, it should look like this. And then we're going to press second and the mode button. That gets us back to our home screen. Now your home screen may have calculations on it. That's okay. I set mine as a blank. It's not going to interfere if you already had performed some other calculations like additions and multiplications before you did this. That won't make any difference at all. So now we have to find the variance. And the variance isn't found on the stat menu, but where we find it is in the catalog of functions. How do we get to the catalog of functions? Well, we hit the second function button and the 0 button. You'll notice that over the top of the 0 button on the TI-83 and TI-84 calculators, it says catalog. So that takes you to a screen that looks like this. There's a built-in function for variance in this catalog. To get to that function, you need to scroll down, but an easier way to do it is to jump to the V's in the list. You'll notice that all of the different keys on your calculator will have a letter on them. We're looking for the letter V, and the letter V is over the number 6. So if you press 6, this list is going to jump down to the V part of our catalog. And you can see that the third option down is the variance. So scroll down and press enter on variance, and that'll put the variance command on your screen. Now this variance command is always the sample variance. So because that's what we're interested in, that's great for us. If we had wanted to find the population variance, we would have to then use the one variable stat screen to get our standard deviation and square it. That would be the other way that we could do this, but this is more precise to find the sample variance. So we need to tell it what list we want the variance of, and that's going to be our L1 list. So we're going to have to type in L1. To do that, we press the second function key and the 1 button, and that'll type in L1. Then you have to end your parentheses and press enter, and when you do that, you'll see this. The variance is 64. That's a really nice variance, actually. And that is the sample variance. This always gives the sample variance. So our variance here, S squared, is 64. Question number 8. Find the standard deviation. Okay, so we've done a lot of work here. To find the standard deviation, remember it's the square root of the variance. So we can take the square root of the value that we just got for the variance, which was 64, and the square root of 64 is 8. So we have a standard deviation of 8. Question number 9. Find the quartiles and the IQR. Identify any outliers. So if we're going to do this by hand, the fact that the data set's already in order is of great help to us. You would find the median, and that would split the data set into 2 halves of data. Then you would look at each one of those halves as an independent data set and find its median, and those would be Q1 and Q3, the other 2 quartiles. Luckily for us, though, we've already entered our entire L1 into the calculator, and the calculator will find the quartiles for us with just a few keystrokes. So we're going to go to the one variable stat screen to help us find the quartiles. We hit stats, and that takes us to the stat screen. We'll use the right arrow key to move the top menu over to the calc menu. And the very first one says one variable stats. We'll press enter. And what that does is it puts the one variable stats command on our screen. If we press enter again, then here are our one variable stats. So you might say, well, I don't see the quartiles. But what we do see is down at the bottom, there's an arrow that's pointing down. That means there's more data there that we can't see yet. So we're going to go ahead and press our down arrow several times, and it'll take us down to where the screen looks like this. And now we can see the quartiles. So the first quartile is 122. The median, which is Q2, is 128. We already found that. And the third quartile is 133. So that's the first part of this question, find our quartiles. Then we're supposed to define the IQR. The IQR is Q3 minus Q1. So the IQR here is going to be 133 minus 122, which is 11. So that's the IQR. We were then asked to find any outliers. To find outliers, we have to use 1.5 times the IQR as our measuring stick, and any data entry that falls more than 1.5 IQRs away from the central portion of the data, the portion of the data that falls between Q1 and Q3, is an outlier. So we take Q1 and we subtract 1.5 IQRs. First, let's compute that. 1.5 IQRs is 1.5 times 11, which is 16.5. So we're going to take this 16.5 and subtract it from 122, and that gives us 105.5. Then we're going to take the 16.5 and add it to Q3. And that's 133 plus 16.5, which is 149.5. So we look for any data values that are less than 105.5 on our set of data, and we find none. And we also look for data entries that are more than 149.5, and we find none. So that means we have no outliers in this particular problem. Question number 10. Find the 95% confidence interval for the mean if you don't know sigma. Well, if we don't know sigma, then that means we have to use a t-distribution to find the critical values. If we knew sigma, then we would use the normal distribution to find the critical values. So, to be able to use the t-distribution, we need to know a few things. First, what are our degrees of freedom? So degrees of freedom, remember, are n minus 1. Since n is 36, 36 minus 1 is 35. And then we also use the level of confidence, which is c equals 0.95. And we turn to the t-distribution. Here's a cutout of the portion of the t-distribution we'll need. So we're looking for 35 degrees of freedom and 0.95 for the level of confidence, and where those two intersect is at 2.030. Now we can find our error, because to build a confidence interval, we need to know the error. So error is going to be TC times S over the square root of n. TC we said was 2.030. The S we had found earlier was 8, and n was 36. Notice we're not using n minus 1, we're using n. When we multiply that out, we get 2.7066666667. We're going to round that to 4 decimal places. So we've got 128 minus the error, 128 plus the error, right? Because we take our point estimate, which is x bar, and we add and subtract the error. And when we do that, our final confidence interval for the mean is 125.2933 to 130.7067. We're 95% confident that the actual population value falls within this interval. Question number 11. Assuming that the population standard deviation is known to be sigma equals 7.5, what is the minimum sample size needed if you want a 90% confidence level for the mean and a maximum error of 1.5 almonds? So we have our minimum sample size formula that says n equals ZC times sigma over E squared. So what's our ZC value? Well, for a 90% level of confidence, it's 1.645. Then times the sigma, which we were just told was 7.5, divided by our error, which is 1.5. We plug that into our calculator. The numerator turns out to be 12.3375 divided by 1.5, which is 8.225 squared, which is 67.650625. When you're dealing with minimum sample size, you always round up to the next highest whole value, any decimal. If it came out even, you leave it. This is not like the class width where you always go to the next highest number, even if it comes out an even value. This one, you just go to the next highest number. If it happens to come out even on its own, then that's your number. But here, this would be 68. So the minimum sample size here is 68. Remember, your minimum sample size always has to be a whole number because you're looking at a number of individual data entries or values, whatever the context of the problem here is. Here it would be 68 bags of almonds. Question number 12. State the null and alternative hypotheses. We've been doing several questions, but in the back of our head, if we read through this problem, this is a hypothesis test. So we're finally getting to the point where we're going to do the hypothesis test based on all the values that we found so far. So to perform the hypothesis test, we need to state our hypotheses. So let's go ahead and look for some keywords here. We see average, at least, 130. Average tells us mu, at least is greater than or equal to, and 130 is the number. So mu greater than or equal to 130. Because there's a statement of equality there, that makes this an H0. So the complementary hypothesis to another hypothesis that has greater than or equal to in it will be a less than hypothesis. So the second hypothesis here is mu less than 130, and that's our HA. So those are the answers for question 12. Question 13. You perform a hypothesis test. Assuming that the population standard deviation is known to be sigma equals 7.5, then at the alpha equals 0.05 level of significance, do you have sufficient evidence to reject their claim? Okay, so we've already got our hypotheses. H0 is mu greater than or equal to 130, HA is mu less than 130, and our claim is the H0 here. That's what came directly from the problem. This is a left-tailed test. The reason we know it's a left-tailed test is because the HA had a less than symbol. Remember, we always look to the alternative hypothesis to figure out our test type. Once we know it's a left-hand test, then we need to find the p-value. So we start with our z-score. Z equals x bar minus mu of x bar over sigma of x bar. So x bar, we found earlier in the problem, was 128. Mu of x bar is their claim. They claimed that the average was 130. And sigma of x bar is sigma divided by the square root of n. We were just told that sigma was 7.5. And the square root of n is the square root of 36. So that's negative 2 over 7.5 over 6, which is negative 1.60. That's our z-score. So we need to go to the standard normal table and locate that z-score. We find negative 1.60 has a table value of 0.0548. Now, we say table value because sometimes the p-value is the table value. Other times, the p-value is 1 minus the table value. And in other situations, it's double the table value. So we need to know which situation we're in here. This is a left-tailed test. And in a left-tailed test, the table value is the p-value. So p equals 0.0548. To make our decision in the hypothesis, we have to do our p-value decision rule, which is basically a comparison between p and alpha. So p is 0.058 and alpha is 0.05. We add a couple zeros to make the decimals the same length, which makes it easier to tell which one's bigger. And in this case, p is greater than alpha. According to the p-value decision rule, if p is greater than alpha, we fail to reject H0. So how do we interpret that? Well, H0 was our claim. So that means that at the level of significance 0.05, we don't have enough evidence to reject H0. So at the alpha equals 0.05 level of significance, there is not enough evidence to reject the claim. What was the claim? The claim that there are an average of at least 130 almonds in their 16-ounce bags. So we cannot reject the claim of the manufacturer. And that's the end to question 13. That ends the section that all refer to the same problem situation. The rest of the final exam will deal with other concepts that weren't covered in those first 13, things like probability and counting and Poisson distributions and binomial distributions and all kinds of other stuff. But these first 13 all deal with the same problem situation. Question number 14. There are 5 people moving towards the checkout stand at the supermarket, and how many different orders can they line up? Well, this is just a factorial. This is going to be 5 factorial, which is 5 times 4 times 3 times 2 times 1. And when you multiply those together, there's 120 ways that these individuals can stand in line. It seems like a very large number, but it is in fact true. If you look back at our notes for this section, section 3.4, you can see we did this problem in the notes, and there was a big long explanation of why it was, in fact, 120. We started with 4 factorial and saw that it was 24, and then we made an argument that said, what if we put a 5th person in, and they occupy all the different positions in the line that they could, and that got us to our 120 different ways. Question number 15. At a raffle, 2,000 tickets are sold for $3 each. There are 3 prizes, 1,000, 500, and 300. You buy 1 ticket. What is the expected value of your gain? So with expected value, we're always looking at the entire situation in terms of our gain. Now, if I won the top prize, my gain isn't $1,000, and that's because I had to pay for the ticket. So I would have to subtract the ticket cost from the prize to figure out my gain. So we're going to make a little table that relates our gain to the probability for that gain. So the table will have the gain across the top, and then the probability. And then for us to find the expected value, we're going to have to multiply each gain to its probability and add those all up. So we'll start with the gains. If I won the $1,000 prize, my gain is $997. If I won the $500 prize, my gain is $497. If I won a $300 prize, then my gain is $297. And if I didn't win, which is far more likely than any of the other things, if I didn't win, then my gain is -3. So what's the probability of achieving each of these gains? Well, 1 person out of the 2,000 is going to win the $997. So that probability is 1 out of 2,000. 1 of the 2,000 people is going to win the $497. And 1 out of the 2,000 people is going to win the $300 prize, which is a $297 gain. So there's 3 winning tickets. The rest of the tickets are losers. So the probability that you lose $3 in this raffle is 1,997 out of 2,000. Because if there's 3 winning tickets, there's 1,997 losing tickets. Now we have to multiply our gains by the probabilities. 997 times 1 over 2,000 is 997 over 2,000. 497 times 1 over 2,000 is 497 over 2,000. 297 times 1 over 2,000 is 297 over 2,000. And -3 times 1997 over 2,000 is -5,991 over 2,000. So the expected value is the sum of x times p of x. We add these up, that's -4,200 over 2,000, which is -$2.10. So we can expect an average loss per ticket of $2.10. Question number 16. The following table represents participants in a recent political gathering. So we have males and females, Republicans, Democrats, Independents. In a situation like this, before we even know what the question is, it's a good idea to add up all your rows and columns. So my first row, 32, 41, and 17, add up to 90. 19, 54, and 22 add up to 95. My first column for Republicans adds up to 51. The Democrat column is 95, and the independent column is 39. Whether you add up the 2 row sums or you add up the 3 column sums, they add up to 185 either way. So all these probabilities will start with a total of 185. What's the actual question being asked? A person is chosen at random from the gathering. What is the probability that the person is a Democrat if we know the person chosen was female? So this is a conditional probability question. If we know the person chosen was a female, then we know they were not male, so we can cross out the entire row that came from male. That also means we cross out the row of values at the bottom that was computed using those male numbers. So this entire bottom row goes away. So our entire universe right now is the female members of this particular political gathering. So what's the probability that the person was a Democrat if we know that they were female? Well, there were 54 Democrats out of the 95 females, and as a decimal, rounded to 4 decimal places, this is 0.5684. That's your answer to number 16. Number 17. A random variable x is normally distributed with mu equals 240 and sigma equals 25. Find the indicated probability. So we're looking for the probability that x falls between 216 and 289. So here we're looking for the area between these two x values. We're going to find the z-scores for each one of these, which will lead us to table values that represent area to the left, and we'll subtract the two areas, and we'll figure out the area between. So we'll start with the larger x value, x equals 289, and find its z-score. So z equals x minus mu over sigma, which is going to be 289 minus 240 over 25. That's 49 over 25, which is 1.96. I'll find the other z-score. So when x is 216, z equals 216 minus 240 over 25. And that's going to be negative 24 over 25. And negative 24 over 25 is negative 0.96. So we have our two z-scores. We'll go to the standard normal table to help us find our table values. So we're going to look for each one of these z values on the standard normal table. We'll start with 1.96. That means we need the positive side of the standard normal table. When we look for 1.96, we find this value, 0.9750. That's our table value for 1.96. For the next z-score, z equals negative 0.96, we need the other side of the standard normal table. And that leads us to a table value of 0.1685. So whenever you're looking for area between, you're always going to subtract the two table values. So the probability that 216 is less than x, which is less than 289, is the probability that the z-score falls between negative 0.96 and positive 1.96, which is going to be 0.9750 minus 0.1685. And when we subtract, we end up with 0.8065. And that's our answer for question 17. In question number 18, 3 out of every 5 Valley teenagers admit to having experimented with some type of illicit drug. 20 teens are chosen at random in the Valley. What is the probability that exactly 10 of them admit to using illicit drugs? So this is a binomial problem, because either they admit to having experimented or they don't. There's two possibilities here. We need to identify all the important values. The n is 20 because we're looking at a total of 20 teens that are chosen. The p is 0.6. Where did we get 0.6? Well, it said 3 out of 5. 3 out of 5 is 3/5. 3/5 as a decimal is 0.6. If p is 0.6, then q is 0.4, because remember that p and q always have to add up to 1. And then we also need the x value that we're interested in for this problem, which is 10, because we're asking a probability question about exactly 10. We can then turn to our binomial probability formula, which is probability of x equals ncx, p to the x, q to the n minus x, and we'll insert these values. So the probability of 10 is given by 20 C10, 0.6 to the 10, 0.4 to the 20 minus 10. So we can evaluate 20 C10, and we can simplify the power on the 0.4. So 20 C10 is 184,756, and the 20 minus 10 is the 10th power. If we enter that into our handy-dandy calculator, we get 0.1171415505, rounded to 4 decimals. The probability that exactly 10 of them admit to using illicit drugs is 0.1171. That's your answer to question number 18. Question number 19. A textile manufacturer produces a certain type of luxury fabric. The average number of missed stitches per 100 square yards of fabric is 3. You randomly select 100 square yards of this fabric. What is the probability that when you inspect this fabric, there are exactly 5 dropped stitches? So this is a Poisson problem. The way we can tell that it's Poisson is that we're looking for a number of occurrences within a set interval of time or space, in this case, space. We need to identify our mu and our x. Mu is the average that we're told, and x is the number that we're interested in finding the probability for. So in this case, mu is going to be 3, and x is going to be 5. So we use our Poisson probability formula, mu to the x, e to the negative mu over x factorial, where mu is 3 and x is 5. So that's going to be 3 to the 5th, e to the negative 3rd over 5 factorial. And when we simplify this, we get 0.1008188134. Rounded is 0.1008. And that is the probability that we find exactly 5 dropped stitches. Question 20. There are 25 people in a restaurant. An advertising firm wants the manager to give 4 of them free meal certificates. In how many different ways can the 4 be chosen from the restaurant patrons? Okay, well this is a combination problem. How do we know the difference between combinations and permutations? Well, in a combination, the order of choice doesn't matter, and in a permutation it does. If I pick 4 people out of 25 in a restaurant, the order that I choose them in doesn't matter because I'm just giving them a free meal card. Whether I give person A the meal card first and person D the meal card last, or I give D the meal card first and A gets it last, the same 4 people end up getting the meal card. So it was irrelevant when we looked at the order. That means this is a combination. If the first person was getting something better than the second person, like maybe they got a free meal for 4, and the second person got a free meal for 2, and the third person got a free meal for 1, and the fourth person got 10% off their next meal, then the order matters because now the prizes are different. But in this situation, the prices are the same, so it's a combination. In a combination, that's NCR. So NCR equals n factorial over r factorial times n minus r factorial. In this case, our n is 25 and our r is 4. So we're looking for 25C4, which is going to be 25 factorial over 4 factorial, 25 minus 4 factorial, which is 25 factorial over 4 factorial, 21 factorial. And that's going to simplify to a whole number. NCRs always simplify to a whole number. And that's going to be 12,650. So there are 12,650 ways that I could choose 4 people from these 25 at the restaurant to get a free meal pass. And that's your answer to number 20. That's basically how the test is going to look. The questions are going to be similar. ask you similar types of things. It's going to cover everything we've done all semester. We've had to leave certain topics out because there's just not enough time to do everything. There won't be any correlation on this final exam. That's a very time-consuming kind of a question, so I didn't want to put one on here because that would take up a big chunk of time. There are other things that also aren't covered here, but this is a pretty broad overview of all the things that we've done this semester. So I wish you luck, study hard, and have a great day.